Yeah, today we're gonna talk about a different topic. So the previous times we talked about graph algorithms and basic ways to manipulate graphs. We started with DFS and BFS. We went to like something like DSU where we could um essentially join and find the parent for each like and basically support those operations really quickly. And then we talked about like minimum spanning tree algorithms, shortest path algorithms. And then finally, we talked about how to find the lowest common ancestor within a tree, which allows us to efficiently compute path queries and yeah. Today we're going to stop talking about graphs and start talking about some a different side of competitive programming, which is data structures. Data structures are essentially, data structures are essentially a way to process data efficiently. So, for example, remember the DSU that we did in the first lecture? That DSU is actually a type of a data structure. Essentially, it supports many different operations. In the case of a DSU, it would be join and finding the root, and it like we can just like use those functions efficiently and use it to optimize our problems. And so many problems are what we call data structure problems, where all we need to do is to optimize a naive solution and use a data structure to do so, and then through the data structure we're able to get a more efficient solution. um yeah, and many data structures are already within the C++ library, like for example sets, multisets, maps, priority queues, stacks, stuff like that. Other data structures you would have to implement yourself, like the ones we're going over today, like prefix sums, or some more advanced ones, binary index trees, for example, or even segment trees and stuff like that. So, um, yeah, those are data structures. Data structures can be used to do a vast amount of different problems, including but not limited to something like supporting fast range queries with or without updates. So you could do fast range queries with updates. You could do fast range queries without updates. You can do various different types of queries, like distinct number queries, sum queries, GCD queries, min, max, stuff like that. Finding paths in a tree fast. So for example, in the last lecture, I mentioned two algorithms at the end. Both of them are essentially a type of data structure, centroid decomposition and heavy light decomposition. Both allow you to find paths within a tree fast. Centroid is essentially like a divide and conquer, and HLD is essentially a segment tree on broken up portions of the tree. Connected components, we've already talked about that with DSU, and maintaining queues, stacks, priority queues, stuff like that. Keeping ordered sets and querying for positions, something like a segment tree or something like a set would be able to do that. And we've already covered some of them, but we will go over a little bit more of how to do the other ones that were not covered. So what we're covering today is to support fast range queries without updates, specifically fast like sum or XOR queries, and also keeping ordered sets and querying for positions, um, something like that. Yeah. So first, we're going to talk about some built-in data structures. Built-in data structures include the queues, priority queues, and stacks that we talked about during the BFS DFS lecture, but they also include sets and multisets. And sets are actually a very powerful built-in data structure. And the reason it's so powerful is because even though there are some other data structures that you could theoretically code and have all the same functions as a set, the set is already built into the library. So you don't even need to code it. So you can essentially get a data structure for free from the library. And it supports, like, for example, erasing, it supports inserting, it supports finding, lower bounds, upper bounds. And a lot of these operations are extremely powerful. And we'll see like I guess, examples of how these operations, how these set operations would work. But it's extremely powerful, and the like a little bit of the way that it's done is they essentially maintain a balanced binary search tree in the background, but because it's using a binary search tree, every one of these operations run in log n time. So what you need to know is it can do all of these operations, really cool operations, and all of the operations will take O of log n time. Yeah. And sets are very powerful. They can be applied in many places. Most commonly, they're applied in simulation problems or any problem that requires you to maintain a group of elements. So for example, maybe sets could be an alternative way to implement Dijkstra's, or it could be a sweep line, or just part of a simulation algorithm. Anyway, sets are very, very powerful. And the difference between sets and multi-sets is that sets, when you insert the same element, it does not do anything. So for example, if you already have a 4 within your set and you wanted to insert another 4, it won't do anything. But with multi-sets, it'll store extra copies of the 4. So if you already have a 4 and you insert another 4, it'll store 2 4s instead of just 1. So yeah, that's essentially set or multi-set. The other important built-in data structure is a map. Maps are also extremely powerful, and they can support similar operations as sets. Again, they're implemented in a similar way, so it's always O of log n per query, but has some additional capabilities. Essentially, what a map does is it stores pairs of keys and values. So for each key, there's a corresponding value, and the key is essentially like something that you input. So for example, if you have a map going from pairs to ints, the key would be a pair. So it could be like, for example, 1 2, and 1 2 would go to like whatever you want it to go to. And so the map essentially, it's kind of like an array that you can have at most, like you can have it takes O of n memory, so it takes O of the number of elements memory, but it takes log n time to access. But it doesn't run into the problem where if you have a giant number that you wanted to put in the array, it goes out of bounds. In a map, you just add that as a new element. So it's a very powerful algorithm. It also supports finding, erasing, inserting, all of those operations, and is a very powerful data structure that you can use to solve various problems. Yeah. So this is the most common application of sets and maps. Coordinate compression is a great illustration of how sets and maps are used. So let's say you have a lot of coordinates and the coordinates go really big, up to like 10 to the 9, right? So you won't be able to store all of those coordinates within an array. But let's say you only had n coordinates, and all of those n coordinates, they don't matter themselves. Only the order of the coordinates matter. Only the like, this one is smaller than that one matters. And if they're the same, they have to stay the same. Like, of course, right? And so how would we do that? Well, the most simple way to do that is to use actually a set and a map. So we first iterate through all of the elements in order and add them all to a set. What this does is essentially it stores all of the elements in sorted order without any duplicates, which is exactly what we want to do, right? And then after that, we iterate through the set and we mark each different number with its new coordinates. So for example, if our set contained 1, 2, 5, 7, then we mark 1 with 0, 2 with 1, 5 with 3, 2, and 4 with and 7 with 3. And then what we would be able to do is we would be able to essentially have essentially remap all of the 1, 2, 5, 7 into 0, 1, 2, 3. And the way we do this is like, or the way we store this is we use a map. So we basically iterate through all the elements in the set and then add all of those elements to a map. And once we have all the elements within the map, we just go back through the original array, and then we change all the elements from that element into what the map tells us to turn it into. So it's a very powerful way, or it's a very clean way in order to coordinate compress a set of coordinates. And yeah, it's a very nice, it's also a very nice illustration of how you would be able to use sets and maps to solve problems. Yeah. The other topic I'm going to talk about today is prefix sums. So the idea behind prefix sums is, let's say you want to answer some range query problems. You're given an array, you want to efficiently query the sum of all elements within a range, like for example, A to B. Using prefix sums, we can actually do this in O of 1. And the basic idea is essentially to define the prefix sum to be the sum of the first like A elements. So the sum of elements 1, 2, 3, all the way up to A. Then it's easy to see that a range query from A to B would just be prefix sum of B, which is 1 through B, minus the prefix sums through A minus 1, 1 through A minus 1. And this is because all of the first A minus 1 elements cancel, and all you're left with is from A to B. So all that remains is we just need to efficiently pre-compute P sum of I. And that's actually easy too, because before we can just do an O of n pre-computation, right? P sum I equals P sum I minus 1 plus element I. And so the pre-computation is just O of n, and we can just store it all in a separate array. And once we do that, we can have efficient O of 1 query per for a range query using prefix sums. Although prefix sums does have its own drawbacks, because we are relying on the formula P sum of B minus P sum of A minus 1, using an operation like min would not work, because you can't reverse a min, right? Because if the min is the same, how do you know what the element was before that? And so min won't work, and like because and min doesn't work because min doesn't work because we're not able to reverse or invert the operation. So we need to be able to invert the operation, and the operation needs to be associative, which means like we're able to do 1 to B and then just get rid of 1 to A, right? So yeah. While many problems do not directly ask for range queries, they may require you to do them. Like, for example, a naive solution may take O of n squared, but O of n, like n of that n squared, can be reduced by prefix sums, and we can reduce the problem to O of n. That's just one example of a way prefix sums can optimize your solutions. There are many other examples. Like, for example, if you have like a giant table and you wanted to like calculate like rectangles within that table, you can also reduce that time complexity. There's a lot of powerful ways to use this technique to optimize problems, and generally, as long as you don't have to have updates, and all you need to do is to find like sum or XOR. Pretty much sum and XOR are the only ones. Maybe multiplication too, but sum and XOR pretty much, and matrix multiplication, I think, too. But besides that, all you can do is besides that, you can do a lot of different things with it. Like you can optimize in grids, you can optimize in single dimensions, and you can optimize it using a variety of techniques or a variety of different ways to use prefix sums. You can have prefix sums on like really strange areas, and you would still be able to use the technique. I did mention, though, that you could use prefix sums in multiple dimensions. How would you do that, though? Like, let's say you had a grid of like, yes, let's say you have a grid and you wanted to efficiently query a rectangle. How would you do that? Well, what you would do is you would essentially like define the prefix sum a little differently. So your prefix sum would be the rectangle consisting of the first I rows and first j columns, right? And that rectangle would be would be very helpful because we can define all of the rectangles within the grid in terms of 4 different rectangles. So we get a few formulas. The first one is you can prove that p sum of ij is a of ij plus p sum of I minus 1j plus p sum of ij minus 1 minus p sum of I minus 1 j minus 1. And the intuition behind this is essentially like how many times are we covering each point within the grid, right? So we want to cover all of the i's and j's less than or equal to I and j. So we definitely want to include a of ij, and we also want to include p sum of I minus 1j and p sum of I j minus 1. But we do notice here that this overcounts. And what does this overcount? This overcounts the rectangle where it doesn't include row I and row j. So from 1 to I minus 1 and 1 to j minus 1. Well, that's simple because we've already computed that. So we can just subtract that. And so now we're left with a formula which we can compute in O of 1. So once we do that, we can pre-compute everything in O of n squared um and do every query in O of 1. But you might ask, wait a second. You did the prefix sum, but how do you do the query? The query is also done in a similar way. We do the same technique of like counting, right? So we for A2, B2, we obviously want to include that because we want to include the rectangle. So now we need to subtract out the rectangle to the left of the rectangle. So A2, B1 minus 1, and the rectangle above it. So A1 minus 1 and B2. But that leaves us with like counting some things a negative amount of times, right? Because we counted it here, but we didn't count it, or we subtracted it here and subtracted it here. So we have to add it back. And this actually also works. So this is another way to do 2D prefix sums. And this is not limited to dimensions or rectangles. You can also do prefix sums on like diagonals, for example. Like if you do a prefix sum over a diagonal, it would just be p sum of ij equals a of ij plus p sum of I minus 1 j minus 1. And that might be helpful in a lot of different problems. Yeah, basically, if you're ever able to have an efficient recurrence based on p sum and there's a very defined order, you can pre-compute it really efficiently. And then once you pre-compute it, you should be able to derive, like, for example, a triangle or whatever the shape that you want to do in the prefix sum is. You should be able to derive that out of the prefix sums that you pre-computed. So yeah. Oops. Okay. Well, we have a little bit of time, so we're going to, I guess, do some problems. This is a Yusaku problem. It is actually a pretty it's a pretty easy maps problem. So essentially the idea behind this problem is that we don't care about any of the letters beyond the first 2 letters of the thing. So we can essentially inside our map input the first 2 letters as the key, and then we have a vector containing all of the first 2 letters of the other things. And then after that, we just go through each individual key, and then we see if like how many there are, and then yeah, that's basically how you do it. Yeah, it's a pretty intuitive problem. Like once you know how to do maps, this should be a pretty easy problem to do. It's not actually that interesting either. So let's do a little bit of a harder problem. Let's see. not this problem. Let's do this problem. So this problem uses the ideas of prefix sums, right? So with this problem, essentially what you're being asked to do is you have a bunch of rectangles and you want to update each range of the rectangle by one, and then you want to figure out how many of the squares are covered, is it at least k or exactly k times. So how many of the squares within the grid are covered exactly k times? And this actually uses a prefix sum technique that I didn't quite say, but the idea is if we can do a range update, right? If we can do a range update, we can also do a range wait. Yeah, if we can do a range, or if we can do a range query and no updates, then we can do range updates. And what we can do with range updates is, let's consider the one-dimensional case first, right? Let's say it's one-dimensional and you wanted to update ranges, right? What you would do is you would update the first, like, if you wanted to add one to everything from A to B, all you would do is in the difference array at A, you increase it by one. In the difference array at B plus one, you decrease it by one. After you do all of the updates, you can essentially just run a prefix sums on that. And what you'll notice is that when we add one to A and subtract one to B plus one, then everything from A to B gets increased by one when we do the prefix sum, but everything after B doesn't get impacted, and everything before A doesn't get impacted at all either. And so this is actually a pretty clever way of being able to do some range updates. So how do we extend this to 2 dimensions? Well, essentially what we would be able to do is we would go from 1, 1, right? Like for example, in the sample, we'd go from 1, 1, we would add 1 to that. Now we need to subtract it out in such a way that it won't impact it beyond 1, 1. And that might seem like, or beyond 5, 5, right? And that might seem a bit hard to do, but there's a trick here. And the trick is that we can update 4 different points, because each rectangle has 4 different points, right? And if we choose the 4 points very carefully in a similar way as the 2D prefix sums, then we can actually be able to solve the problem. So how would we choose those 4 points? Well, let's take inspiration from the original prefix sum, original 2D prefix sums, right? Here we're using this, like an idea like here, this is plus, minus, minus, plus, and it's plussing at the 2 endpoints, which are on like the quote unquote main diagonal, and it's subtracting at the 2 endpoints that are not on the main diagonal. Let's try that here. So if we add 1 to 1, 1, if we add 1 to 6, 6, we subtract 1 to 1, 6, and we subtract 1 to 6, 1, how will that impact the contribution to like a particular number? Well, let's say it's within the rectangle. Then it'll include the 1, 1, right? And that'll increase by 1. So we already established that within the rectangle, we're all fine. Now, what about above the rectangle? Well, if you're above the rectangle and you're still to the left of the right endpoint, then you're gonna get the -1 from the 1, 6, and the +1 from the 1, 1, so you get a 0. And that's perfect. If you're to the right of both, then you'll get 2 from the 6, 6 and the 1, 1, but you'll subtract 2 from the 6, 1 and the 1, 6, and then that'll cancel out to 0 too. And similarly to the right, it'll also be 0 because you're gaining 1 from the 1, 1, but you're losing 1 from the 1, 6, or from the 6, 1. So everything where it's outside of the rectangle is updated by 0, and everything within the rectangle is updated by 1. So this actually works. So our final solution is going to be, every time we see a rectangle, we update each of the endpoints. So at 1, 1, we updated it by 1. At 1, 6, we updated by -1. At 6, 6, we updated by 1. And at 6, 1, we update it by -1. And then we do that for every rectangle. After we do that for every rectangle, we can do a prefix sums on the whole array. After we do the prefix sums on the whole array, then we'll be able to figure out that at like a point X, like at any point X, how many coats of paint are on point X. And once we know that, then we just iterate through every single point within the grid, and then we're able to, once we iterate through every point within the grid, we're able to basically count the number that have exactly K coats of paint. And so this is a pretty nice problem to illustrate the power of 2D prefix sums, that not only can it do like range queries, range sums, whatever, 2D, right? It can also do 2D range updates. And similarly, it can do 3D, 4D, 5D. It can do range updates. It can even do range updates and range queries, provided all of the updates are before all of the queries. And it can do a lot of really powerful things just with the basic idea of finding the rectangle that goes up to it, or finding the some of the first few elements, or finding the the first few in the diagonal, or whatever the shape that you want to make is. You can probably use prefix sums for it. Yeah, I think time is up, so yeah.